begin examining our slide of the molecular view of elements and compounds, we understand in the classification of matter, matter can either be pure or a mixture, and this slide is emphasizing that pure substances are either elements or compounds. Elements, of course, can be atomic, as in this example of a single atom of neon. Notice just one atom in the blue section there, where they can be molecular in terms of oxygen, O2. So molecular elements are atoms of the same element bonded together covalently. Atomic elements are those atoms that are most stable in nature just by themselves. Compounds, of course, are bonded to two different styles. We will see ionic bonds or covalent bonds. Ionic bonds give rise to ionic compounds, and this example is sodium chloride with a basic formula unit of NaCl. A molecular compound built of two nonmetals, such as water, H2O, held together by sharing electrons. So as we examine the classification of elements and compounds, it really has two focuses. Are the atoms alike or are they different? Are the atoms held together by ionic bonds or by covalent bonds? We begin examining atomic elements, those elements whose particles are just single atoms, as in the focus in the previous slide of neon. Molecular elements, those elements whose particles are in multi-atom molecules. The previous slide showed the diatomic molecule of oxygen, O2. And in nature, we'll see that there are 7 diatomic molecules. So elements, the simplest form of all matter, either in atomic or molecular form. Or compounds, coming 2 styles as well, molecular compounds and ionic compounds. Molecular compounds are those whose particles are called molecules, composed only of non-metals. The non-metals covalently bonded together. Ionic compounds are compounds whose particles are cations and anions. Cations are positive metal ions who have lost electrons, and anions are negative ions from nonmetals who have gained electrons. Ionic compounds are held together by electrostatic attraction. Positive and negative charges, according to just the basic law of electricity, being held together by opposite charge attraction. Now elements, most are in single atom form. Most elements have their single atoms being their constituent particles. So the vast majority of elements on our periodic table are found as single atoms. The atoms may be physically attracted to each other, but they're not chemically bonded, and those attractions may be due to intermolecular forces that are coming up later in our chapter as well. But a few elements have molecules as their constituent particles. So elements are like atoms that might be bonded together, giving us a molecular form of the element. So those molecules that are made of 2 or more atoms chemically bonded by what's called a covalent bond, by that sharing of electrons. Here are 7 diatomic molecules, and I made mention of a funny sentence: horses need oats for clear brown eyes, is a sentence that puts those 7 diatomic molecules right in order from our periodic table. In nature, we never find just an atom of H, hydrogen. It's just too unstable, too highly reactive, so it will either bond to a different element to create a compound, or it will bond to itself to create a diatomic molecule of that element. The rule of 7s is telling us that each of these 7 elements in nature exists in a diatomic form. In nature, nitrogen is never found as a single atom. It will either be bound to another element, creating a compound, or bound to itself to create a diatomic molecule. N2 is nitrogen. The air that we breathe is O2. Oxygen is one of its major components. Fluorine, F2. Chlorine, Cl2. Bromine, Br2. and iodine, I2, those 7 naturally occurring diatomic molecules. And again, I'll repeat this funny sentence. Hopefully it will stick in your mind. Horses need oats for clear brown eyes. Places those 7 elements into a sentence that are easy to remember. There are other elements that even have larger molecular structure. Instead of just 2 atoms known as diatomics, sometimes we have elements in polyatomic form. Phosphorus in nature is found with 4 atoms of phosphorus held tightly together. Sulfur is S8 and selenium as well is S8. 8 atoms of like elements bound together. And this slide shows those 7 naturally occurring diatomic molecules, diatomic meaning 2 atoms bound together, and then elements that exist in polyatomic are shaded in pink. Horses need oats for clear brown eyes. That funny sentence that allows us to begin to memorize those 7 naturally occurring diatomic molecules. If we start connecting atoms to create compounds, those atoms are of different elements. And again, they'll come in 2 forms, ionic compounds or molecular compounds. The first are ionic, some compounds that are composed of ions arranged in a 3-dimensional pattern. These are known as ionic compounds. This 3-dimensional pattern are often called a crystalline lattice. These are salts in nature, formula units commonly called the word salt, where we see this repeating pattern of an array in a 3-dimensional structure called a crystal. Each positive ion, called a cation, being surrounded by the negative ions, and they just repeat the pattern over and over until you create a large, beautiful crystalline structure. Other compounds are composed of individual molecular units. When nonmetals combine with nonmetals, they're attached by covalent bonds. Ionic compounds, the first, are positive and negative ions where we'll see a transfer of electron in an ionic bond, whereas molecular compounds are 2 nonmetals attached by covalent bonds, where electrons are being shared. On a molecular level, notice propane. Now propane is what we use to turn on our gas grill, C3H8. There's 3 carbons in a chain, and each of those carbons have hydrogens hanging off of them to create a hydrocarbon molecule known as propane. They are held together by covalent bonds. Carbon is a nonmetal. Hydrogen is also a nonmetal. When nonmetals combine, they create molecules. This is a gas at room temperature. Now, compared to an ionic compound, sodium chloride is regular old table salt. Sodium ions have formed when a sodium atom lost an electron to become a cation. And chloride formed when a chlorine atom gained an electron. Sodium plus is electrostatically charged, attracted to chloride, who is also electrostatically charged, 1 positive being attracted to 1 negative, and we start to see a repeating crystalline array of positive, negative in a large 3-dimensional structure. Let's classify each of the following as either an atomic element, molecular element, molecular compound, or ionic compound. Take a moment and let me just review those definitions, and you'll pause the video and jot your answers, and then we'll check together. An atomic element, those elements that are existing in nature as a single atom of 1 element. Molecular elements are when elements of the same type are bonded together. Molecular compounds have 2 or more nonmetals of a different variety of atom bonded together. An ionic compound, metal to nonmetal hooked by electrostatic charge. Pause the video and write down your guess and come back and check when ready. Let's see how you did. There's aluminum, a single element, just a symbol all by itself, would be classified atomic element. Aluminum chloride. We have a metal, aluminum, hooked to a nonmetal, chlorine. When a metal and a nonmetal hook, we call it ionic. Chlorine are two atoms of the same element bound together, molecular element. Acetone, nail polish remover. Acetone has carbons, hydrogens, and oxygen bound together. Atoms are all nonmetals. C's, H's, and O's all are in the nonmetal family, molecular. Just as carbon monoxide would be molecular. C and O are both nonmetals. Now here's a big difference. See, cobalt, capital C, small o, very different. It's an element made of one atom. Now above, notice the importance. C, capital O, gave us carbon oxygen, molecular compound. Just another opportunity to stress the importance of how to write a correct formula or symbol using capital letters and small letters when appropriate. Ionic compounds. Thinking about the metals losing and the nonmetals gaining electrons, we start to consider how ionic compounds come together to create an electrically neutral compound. When metals combine with nonmetals made of ions, metals, those elements that are always found to the left of our periodic table, to the left of that border that separates metals from the nonmetals, they will always lose electrons to form cations. Nonmetals, those to the right of our border, will always form negative ions called anions. Positives and negatives come together to create an ionic compound. So no individual molecule units, instead they have a three-dimensional array of cations and anions. Each basic building block that is a repeating pattern in a larger crystalline structure is known as a formula unit. The smallest whole number ratio of the repeating pattern in a larger crystal structure is called a formula unit. Now sometimes ionic compounds are built of what's called a polyatomic ion. If it's made of a single element carrying a charge, we call it a monatomic ion. If many atoms are bound together acting as a unit carrying a charge, they're called polyatomic ions. And they're named very differently than a monoatomic ion. So it's still the same set of rules for hooking positive to negative, except now we've invited more players on the field. The polyatomics will also be used to create compounds. Compounds that contain ions are called ionic compounds. As a whole structure, they have no total charge, but they're built of positives to negatives that are electrically balanced, so the net charge is always zero. When a compound has no total charge, but the individual structures, those ions, are indeed charged, we start to consider that for every one positive cation charge, we need one negative anion charge to neutralize, to give us the net charge of zero. If sodium ion, who's written as Na+1, showing its loss of one electron, is combined with a sulfide ion, here the "ide" I'm trying to emphasize, the element is called sulfur. The ion now will end with IDE, showing that it's a negative ion, and it gained 2 electrons. Sulfide is S-2. Well, if sodium has just one positive and sulfide has 2 negatives, it's not electrically balanced if one sodium were to combine with one sulfur. It still would have a net negative charge. How many sodium ions, each at a +1, would be required to neutralize the charge on a sulfide who carries a -2? Well, you can see in this slide it's showing us that 2 positive sodiums are required for the 1 negative sulfide, and the formula would become Na2S, sodium sulfide, a binary ionic compound. Here is a slide that will represent those step-by-step instructions for writing ionic compounds. And let's review these guidelines or rules one at a time. We're being asked in this example to write a formula for the ionic compound that would form between calcium and oxygen. Well, step 1 says, let's write the symbol for the metal cation and its charged, followed by the symbol. So positive ions are always written first. Metal first, non-metal last, just by convention, so we're doing it all the same way. Now take a moment. Where is calcium on your periodic table? It's number 20. Locate it. It's in group 2A, period 4. Ca is its symbol. Calcium in group 2A has 2 valence electrons. 2 electrons in its outermost energy level. When calcium goes from an atom to an ion, it will lose 2 valence electrons. Loss of 2 electrons results in a positive 2 charge. So when we write the symbol for the metal cation, Ca, we'll denote its charge as a positive 2. We're being asked to create a compound who's the anion of oxygen. Now, oxygen is the name of the element. It's number 8. Its symbol is O. Locate it on your periodic table. Element number 8 is oxygen. It lives in group 6A, period 2. Group 6A tells us that it has 6 valence electrons. When it wants to become a noble gas, look down the row. See where neon is? It's noble gas at the end of the row, Ne. It needs to gain 2 electrons to become more stable, like the noble gas neon. A gain of 2 electrons results in a negative 2 charge. The element oxygen forms the anion now known as oxide. Here the IDE, oxide. Calcium needs to lose 2 electrons. Oxygen wants to gain 2 electrons. We see the forming of a beautiful relationship where the metals will transfer their electrons to the nonmetals in what's called ionic bonding. Calcium plus 2, oxide minus 2. We obtain the charges from the element's group number on the periodic table. Number 2, adjust the subscript on each cation and anion to balance the overall charge. Well, with our first example, a plus 2 does indeed neutralize a charge of a negative 2. A plus 2, when added to a negative 2, gives us a net charge of 0. So the subscript ratio of 1 to 1 does indeed create a neutral compound of CaO. The name? Calcium oxide. Step 3 is just a double check. Is the sum of the charges equal to 0? The cation charge of a positive 2, the anion charge of a minus 2 do indeed cancel to give a net charge of 0. We formed a compound called calcium oxide, CaO. When writing formulas for ionic compounds, always write the symbol for the metal cation with its charge first. The metal ions always go first. Then write the symbol for the nonmetal anion with its charge. The nonmetal will always be placed last. Charge without the sign becomes the subscript for the other ion. A general rule just simply says crisscross the charges and those become your subscript. Of course, reducing those subscripts to the smallest whole number ratio. In the previous example, Ca was a plus 2, O was a minus 2. If we had indeed crisscrossed the charges and made those the subscripts, the resulting compound would have been Ca2O2. But that 2 to 2 subscript ratio needs to be reduced to the lowest form possible, and that's why it was written as 1 to 1, CaO. With formula units, the smallest whole number ratio will always represent our chemical formula for ionic compounds. The last rule, of course, is simply a double check. Double check the charges and indeed write out, make sure that they are adding to 0. Let's take a look at this example. Writing the formula of a compound made from aluminum ions and oxide ions. I have the 5 steps written here, and let's go through them one at a time. Number 1, write the symbol for the metal cation in its charge. We have to go to the periodic table and search for aluminum. Now look where it is, aluminum, number 13, its symbol, Al. What charge would aluminum be carrying? It's a metal found in group 3A. Aluminum, always metals lose electrons. Column 3A, it will be a positive 3 charge. Aluminum with a +3. Smart idea, just on your periodic table, write that charge right in the box of aluminum, and you don't have to worry about remembering its charge if you've written it right in the box. That's a great idea. Write the symbol for the nonmetal anion and its charge. Well, the anion is oxide. Here the IDE, negative elements, negative ions end with "ide." The element's name is oxygen. Its negative ion is now called oxide. Find it on the periodic table. See where it is? It's number 8. The symbol for oxygen is O. When it forms an ion, look to see where it lives. What group number? Well, it's found in group 6A. How many electrons will oxygen need to gain to become like a noble gas? You got it. It needs to gain 2 electrons, forming a charge of a -2. O -2 from column 6A. If a +3 connects to a -2, we are not electrically neutral. If a +3 and a -2 combine, the 1-to-1 subscript ratio does not work. But let's bring those charges around and down to make the subscript on the other element. The +3 on aluminum tells me the subscript on oxygen will be a 3. The -2 on the oxygen tells me aluminum subscript will be a 2. Bring the charges around and down, crisscross, bring them down, not the sign, positive or negative, because subscripts are simply telling me quantities, not a charge, but a quantity. Al2O3 is the binary ionic compound called aluminum oxide. Notice aluminum, we have 2 of them, each carrying a +3 charge for a net +6. Oxide, we have 3 of them, each carrying a net -2 for a total of a -6. Al2O3 does indeed add to 0, aluminum oxide. This is a very, very important skill, writing formulas based on charge. Here are some examples. I'd like you to actually pause the video with these 3 examples and work to find the correct chemical formula and the correct name by putting positive and negative together. Name them as well. Take some time with your periodic table and practice this very important skill, and start the video again when ready to check your work. Here we have potassium ion with a nitride ion. Potassium symbol is K. It's in group 1, so it will be carrying a +1 charge. Potassium ion with a nitride ion, N, is in group 5A. It had to carry a -3 charge. Did you write K3N? Potassium nitride. Ca with a +2, Br was a -1. When we crisscrossed to neutralize charges, calcium bromide, CaBr2. Aluminum ion with its +3 charge. Sulfide ion with its -2 charge. The formula for aluminum sulfide, Al2S3. We are writing formulas for what are called binary meaning two elements, binary ionic compounds. One metal hooking to one nonmetal, creating an electrically neutral compound. When we are given names and writing formulas, we crisscross charges. What about formula to name rules? Going the opposite pattern. I've been practicing all along with that, but here's the actual formal part of the lesson on how to look at a formula and go about naming it. We understand that ionic compounds have a special set of rules. They'll be different from molecular compounds based on the kinds of elements that we find inside of its structure. To emphasize again, ionic compounds are made of metals to nonmetals, something that's positive hooked to something that's negative. So remember, cations are always written first, followed by the anions, the negatives. Some may have one or more nicknames that are learned by experience. For instance, sodium chloride you hear as table salt, sodium hydrogen carbonate you might call baking soda, but those are nice to know names. We're going to follow the systematic name by naming the ions themselves. Since the positive ion is written first, it gets named first. If the cation is, first bullet says, a metal with invariant charge, simply name the metal. Okay, now let me interpret that. If the metal is a metal that we absolutely know the charge of by where it lives on the periodic table, it does not need a Roman numeral in its name. The elements that fall under that first category, on your periodic table, find the elements in family group 1A. They are hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. I've just listed all of the elements in the first column. We always know that they are going to carry a +1 charge. There's no choice in life. They have a +1 charge when they form ionic compounds. They have an invariant charge, always the same. Group 2A, let me list those for you. Beryllium, magnesium, calcium, strontium, barium, radium. All of those in the second column in group 2A are always a +2 charge. They have an invariant charge, which simply means it's always the same. Aluminum. Aluminum is a metal in group 3A. It is always a +3. Why not write these on your periodic table? Write them in the box so you'll always remember. Just aluminum in that group 3A, just that one and only one, is a +3 charge, always. Let's add some more while we're thinking about it. On your periodic table, find the element zinc. It is number 30. In the box of aluminum, tell yourself that it is always a +2 charge. Always. It has an invariant charge. It will never change. It's always the same. Underneath that one is cadmium. Cd is the element cadmium. It also is always a +2 charge. Write it in the box on your periodic table. One more. To the left of cadmium lives silver, Ag, the symbol for silver. It is always a +1 charge. Write that in the box of your silver. Now here's what we've said. We are trying to write systematic names by naming the ions. We name the cation first, the metals. The first bullet on this slide says, we name the metal with invariant charge by simply naming the metal, the name of the element. I've really gone through carefully and described what the word invariant charge means. Those are the elements that we know the charge just by where they live on the periodic table. First family column, always a +1. Second family column, always a +2. Aluminum, always a +3. Zinc and cadmium are +2s, and silver is a +1. And this is the next important statement. Every other metal, there's a lot of them, have what's called a variable charge. That means we cannot look and know by where they live on the periodic table the charge that they form when they go into compounds. It really depends on what they're hooking to. Sometimes they'll lose one electron and be a +1. Yet if they rearrange and hook to something else, they could be a +2. Sometimes they're a +3. Heck, sometimes they can be a +4, depending upon the most stable arrangement of the nonmetals that they're hooking to. If the metal has a variable charge, we have to name the metal, and by using a Roman numeral, we'll name the charge that it carries. If, the third bullet, if we have a polyatomic involved, poly means many atoms acting together as a group, we'll name the polyatomic ion. Now, one thing you might find handy, and it was listed in the Blackboard Tools under Periodic Table and Tools, you might find handy to print off the polyatomic ion chart just so you have all of the names of the polyatomics along with their formulas very handy as we start naming and building compounds. Polyatomics are not found on the periodic table. Their names are found on a separate table known as the polyatomic ion chart. Lots of rules there for cations. Basically it says, name the ion, name that metal ion, and check to see if it needs a Roman numeral. Once we name the cation, we name the negative ion. The anion is a non-metal. Remember, the element's name has now been changed to end with "ide." If it's a monoatomic ion, it will end in "ide." If it's a polyatomic ion, we find those names on the polyatomic ion chart and we say its name. Say the name of the positive, check to see if it needs a Roman numeral, say the name of the negative, put them together and you've named your compound. When we name metal cations, I'm now stressing some things that we've written on our periodic table. And I've kind of rambled about these, but it allows us to kind of put it onto our slide as well. The metals with invariant charge, those metals that we know the charge just by where they live, they do not change. Here is a list of those. All of the elements found in group 1A, you see, are +1s. All of the elements found in group 2A, you see, are +2s. Aluminum, a +3. Zinc, and I want you to add cadmium underneath zinc, are +2s. And silver, a +1. If we know the charge by where it lives, we do not need a Roman numeral to tell us the charge. We know the charge by where it lives. We simply say the name of the metal ion. If we have a metal ion that has a variable charge, an element that we don't know the charge of by where it lives on the periodic table, we use a Roman numeral when naming the ion. The Roman numeral tells us the charge that it carries, not how many we have in a compound, but the charge. When I hook together, the Roman numeral is the charge that it carries and not how many that appear in the formula. take a look at some examples. Chromium in nature can be a +2 or a +3. How can I tell the reader what chromium I'm hooking with? Well, I do so with a Roman numeral. Cr+2 must be named as the chromium 2 ion. Chromium with a +3 must be named as the chromium 3 ion. Now you see the older Latin words us and ic, the OUS ending always given to the element with the lower charge, the ic ending with the higher charge. We use the Roman numerals in the systematic name. In nature, iron can be a +2 or a +3. We would denote that to our reader by calling it the iron 2 ion or the iron 3 ion. Cobalt will either be a 2 or a 3 as well. Copper in nature is a +1 or a +2, copper 1 ion or copper 2. Tin 2 or tin 4 are the two choices for the tin ion. And lead, of course, lead 2 or lead 4 indicating its charge. Now mercury on this slide is showing a diatomic ion. The mercury with a +1 has two mercury +1s bound together to give a net charge of a +2. That's a unique situation, and I won't spend a lot of time on that, but mercury does have this little asterisk after it there. So Roman numerals are given to the names of elements, those metal ions that we do not know the charge by where they live. They have a variable charge based on what they're hooking to. So as we practice naming monoatomic, nonmetal anions, monoatomic, one atom, nonmetal anions, we simply determine the charge from the position on the periodic table. And I strongly suggest make that periodic table as friendly as can be. Write these notes directly inside of the boxes. Find the element carbon. It's number 6, group 4A. Carbon becomes carbide when it forms a negative ion, carries a -4. Underneath it, silicon becomes silicide. It carries a -4. Notice you stop, you hit the border. Silicon, even though it's a transitional a metalloid, we're going to consider that as a negative ion. But if you hop the border to the element Ge, germanium, you're now flipping to the positive side of the border. Positives are from the left side over, the negatives are to the right side over of that very dark line, the border between the worlds of metals and nonmetals. Nitride carries -3 as well as phosphide, oxide, sulfide, selenide, telluride, all of those elements in group 6A with a -2, and all of the elements down 7A, fluoride, chloride, bromide, iodide, all carrying a -1 charge. Take the time to write those on your periodic table, making the time it takes to write formulas go so much quicker. To name these monoatomic ions, the name of the element gets changed. The last little syllable gets lopped off and we put on the IDE ending. The element's name now ends with "ide" to show that it's a negative ion. When we name binary ionic compounds, binary, 2 elements, ionic, one must be a metal, one must be a nonmetal. The word invariant, we know the charge by where it lives. It does not change. So just kind of pulling apart the slide title, we're going to name binary ionic compounds with metals who always have the same charge. So that means we've got one metal positive, one nonmetal negative. We simply say the name of the positive, say the name of the negative, and the negative will end with IDE. You name the cation first, you name the anion last, knowing that it will end with an "ide" ending. Sodium chloride, calcium fluoride, and so forth. The name of the positive, the name of the negative, ending in "ide." What might the name of CSF sound like? Well, what's the name of the element CS? It's number 55 on your periodic table. What's the name of F? It's number 9 on the periodic table. Well, CS stands for the element cesium. It does not need a Roman numeral because we know its charge always is a +1. Fluorine is the name of the element. The name of the negative ion is now fluoride. CSF is made of cesium atoms and fluorides. So we have a compound called cesium fluoride. Naming the positive, naming the negative, and ending it with IDE. Now you practice. These are all binary ionic compounds that do not need a Roman numeral. We know the charge by where they live. Pause the video and write down the names. Start it up when you're ready to check. Did you write potassium chloride, magnesium bromide, and aluminum sulfide? The names of these binary ionic compounds. How do we go about naming compounds that do need a Roman numeral? Binary compounds that are ionic for metals with a variable charge. Variable means we don't know their charge by where they live. They are transition metals in the short columns in the center, and therefore we have to tell the reader the charge on the ion because it could vary from one compound to another. Very similar rules to the last stuff. Name the positive ion, name the negative ion, end it with "ide," but in the middle of those two names goes a Roman numeral to tell the reader the charge on the ion. So we start with the metal cation first, just name it. Name the nonmetal ion last, ending with "ide," and place between them a Roman numeral in a parentheses. Generally seen it's in a parentheses. I've seen it both ways, to tell you the truth, but in our text you'll see it in a parenthesis. And what that charge, or that Roman numeral is going to tell you is the charge on the positive ion, not how many there are, not its subscript, but the charge that it's carrying. Now sometimes you can be a detective and uncrisscross subscripts to find charges, and that's kind of a trick we'll learn along the way. So we have to determine positive ion, negative ion names ending in "ide, place the Roman numeral in the center, the Roman numeral indicating the charge that it's carrying. Here's an example. I see a compound with the formula Au subscript 2, S subscript 3, Au2S3. Well, step 1, we go to the periodic table and we find the name of the symbol Au. We go to the periodic table and we find the name of the element for S. Au2S, well, the first name of Au is gold. Au stands for gold. S is going to be sulfide. Now the element is sulfur, but the name of the negative ion is sulfide. So kind of thinking through what we have so far, we have gold and sulfide. Alrighty. But what we need in the middle is the charge using a Roman numeral for the symbol Au. It is not the number 2. It is not how many we have, but it's the charge that it's carrying. So let's be a little bit of a detective and go to work finding the charge. Step 1 says, determine the charge on the negative ion. Well, go to your periodic table. You can see that we wrote in the box for sulfur, it's going to carry a -2 charge. How many do you have of it? Well, the subscript tells us there's 3 sulfurs. What's 3 times a -2 gives us a total negative charge of -6, telling us that the total positive charge must be a +6. We know that compounds must be electrically neutral. So if the total negative, 3 units of a -2 give us a total negative of a negative 6, we know the positive must be a total of plus 6. But how many are there? Well, I can see that the subscript 2 tells us there's 2 units giving me the total of plus 6, and I simply divide. 6 divided by 2 tells us that the gold has a plus 3 charge. Now a quicker system for this particular example, uncrisscross. Look at the subscript on the other guy from gold. The subscript on the negative came from the charge of gold. Uncrisscross, and we can clearly see that sulfur was a minus 2. Gold must have been a plus 3. So we're determining the charge, calling that compound gold 3 sulfide. Name the following as a practice. Name them. Turn off the video and see what you find. Find the total negative, work backwards to find the total positive. That becomes the Roman numeral, the charge that it's carrying. Number 2 might be tricky. Give that one a careful thought. The rest I can see is uncrisscrossing, but think about number 2 a little more carefully. Pause the video, give them a try. Here's what we found. Ti is the name of the element titanium. Cl stands for chlorine, but when we name it negative ion, it would be chloride. We know that chloride carries a minus 1 charge. 4 of them must be a total of a negative 4. 4 units of a negative 1 give me a total of minus 4. Therefore, titanium's charge must be a positive 4 to create an electrically neutral compound. We would name this compound titanium, Roman numeral 4, chloride. Second example, it's not as easy as just uncrisscrossing. We know that oxygen carries a minus 2 charge. Look at it on your periodic table. Did you handwrite that in the box? It's a minus 2 charge. 3 units of a minus 2 give me a net of minus 6. Chromium in this example must be carrying a positive 6 charge. The name of our compound, chromium 6 oxide. Nitride, the negative ion in example 3, on your periodic table, you know that nitrogen carries a minus 3 charge. 2 units of a minus 3 give me a net negative 6. So the net positive must be positive 6, coming from an individual charge of plus 2 for each of those 3 iron ions. The name of the compound, iron, Roman numeral 2, nitride. Not how many you have, but the charge that it carries. Iron 2, nitride. Same example idea here, naming binary ionic with variable metal charge. What might the name of CuF2 sound like? Cu stands for the element copper. Fluorine, named as an ion, is fluoride. Go to work finding the charge on the positive ion, and you do so by determining the net negative and working backwards as a detective to determine the total positive per positive ion. CuF2 would be named copper, Roman numeral 2, fluoride. We could see that a positive 2 charge on the copper is going to balance 2 units of a minus 1 on the fluoride. Copper, Roman numeral 2, fluoride, the name of our compound. It's binary, meaning 2 elements, ionic, meaning one's metal and one's a nonmetal. Binary ionic compounds, simply name the positive, name the negative, check to see if it needs a Roman numeral. Now, of course, we've tackled this example just verbally before as we found the positive charge. So these examples now being written with the name, titanium, Roman numeral 4, chloride. Lead, Roman numeral 2, bromide. iron 3 sulfide. Naming binary ionic compounds for those that need a Roman numeral. What if we go the opposite direction and we're looking at a name and want to turn that into a formula? Following those steps, manganese, Roman numeral 4, sulfide. Well, the Roman numeral tells us the charge that it carries. So Mn, the symbol for the element manganese, carrying its positive 4 charge. The symbol for the negative ion S, the element's name is sulfur, so the anion sound is the sulfide. You find it on your periodic table underneath oxygen in the box. Did you tell yourself it was a -2? We've got a +4 hooking to a -2. Remember, we can crisscross those subscripts and find, or crisscross the charges and find the subscripts, but remember, we have to reduce them down. So Mn2S4 is a good start, but it would be marked incorrect because that 2 to 4 ratio can be simplified by a 1 to 2 ratio. So manganese, Roman numeral 4 sulfide, MnS2, the lowest subscript ratio possible when the +4 hooks to a -2. And the double checking does indeed show that we've neutralized electrically to balance to 0. What would the formulas for the following compounds look like? If a copper 2 hooked to a nitride, an iron 3 hooked to a bromide. Please pause the video. Try these out. Don't cheat yourself to practice. It really pays off. Start up again when you're ready to check your answer. Copper with its +2, nitride with its -3, we crisscrossed. Copper 2 nitride, Cu3N2. Iron 3 with a bromide. Iron, Roman numeral tells us it's a +3. Bromide, right in that 7th family, fluorine, chlorine, bromine, iodine, in that 7th family, we know it to carry a -1. Crisscross, and we come up with FeBr3, iron 3 bromide. This might be a good place to pause. We're going to need our polyatomic ion chart. You might need to print one. It would just play so much invaluable here. So let me pause the video and give you an opportunity to gather that chart and start up again when ready.